My name is Nathan Patrick Helton. I'm from the red team, and in lieu of a presentation on any kind of experiment, I'm going to be giving a little bit of a talk about chemical vapor deposition. Some of you in this room may not know, a few weeks ago, Mr. Ryan Tuggle gave a lovely presentation on carbon nanotubes. And in his presentation, he shortly discussed one of the methods that they produce carbon nanotubes, chemical vapor deposition. And some of us were a bit curious as to what goes on with chemical vapor deposition, what it is, the different methods, and why we should care. So a little bit outline of what I want to talk about today. I'm just going to talk about the general methodology that is used in chemical vapor deposition, and then a few specific methodologies that are a slight variation of the general one. And the reason I chose these specific ones to discuss is because they are, quite frankly, the ones I found the most information about. And they seem to be two of the most used ones in industry and other applications. And I'll wrap it up really quickly with a very brief discussion of chemical vapor deposition in the future. Just an outline of what chemical vapor deposition is. Basically, you'll get a volatile gas precursor that will go into the reaction chamber. This reaction chamber is heated with a furnace or other such things, and the volatile gas will either react and form a precipitate that will fall on a wafer substrate, or it will just fall naturally or through other various means. And these wafer substrates, it'll the thing in question that we're interested in that falls on the wafer has an affinity for the wafer by either short, weak hydrogen bonds or other things on that kind of level, and it will stick to the wafers. And then because if some of these gases stick around, they can harm the equilibrium, and they're generally not nice, so you need a nice pump to get them out of there whenever they're done. And it used to be that this was done in atmospheric pressure, but in most modern applications, it is either done at LP, which is low pressure, or UHV, which is ultra high vacuum. And most modern applications use that. And one of the variants of chemical vapor deposition I'm going to be discussing today is atomic layer chemical vapor deposition. And why is it beneficial? Why do we use atomic layer? And that's because we can use atomic layer deposition to be very precise in the kind of substrate and the kind of layers we want to form on our substrate. We can have precision down to the angstrom or the micrometer level. And this is just this picture here is a little diagram of what's happening. You can see we have a nice substrate that chemical that bonds to the substrate. Then you have other chemicals that will bond and will have reaction. And I'll discuss that a little bit more in just a second. So here is what's happening on the atomic layer. This is not happens in all of them, but it's just an example. And you see the precursor can come down, and you will have it'll expose to the substrate, and it'll stick. And then you don't want it to stick around, so you will wash it away with a pump. And then you can get and then you also get byproducts and stuff, and you'll want to wash those away, reactants, and over time you'll get several layers that form up. And because you're going to be putting in a precursor and byproduct and pushing it out, they developed this method that they call vapor pulses. Well, they'll send in a vapor of one kind and a pulse and then a next. And the alternating pulses is how you develop the alternating levels in this, and one way to develop that. And this picture just shows that this does actually work. It's not just theory. This is an actual picture on the microscopic scale of what's happening. And then why should we care about atomic level chemical vapor deposition? Well, it is used in electroluminescence, like the ones you will find in your car dashboard at night. It's also used in DRAM, dynamic random access memory in your computers, very important, and other such microelectronic applications. And then another type of chemical vapor deposition that I focused on, which based on my research seems to be one of the most often used one, and it has a couple different ways of going about getting about getting the plasma. It's called plasma enhanced chemical vapor deposition. And one way to get the plasma is to use microwave electromagnetism to heat up the gas so that it goes into the plasma phase. And then because you want the plasma because that's where your reaction occurs, or so you can get the substrate, the particulate that falls down on the substrate. And then there's just general plasma enhanced, which is done with electromagnetic pulses or other such mechanisms. And the thing about general plasma enhanced is that the wafer will be heated as well. The plasma area will include the wafer, so that could or could not be beneficial. And the difference between general plasma enhanced and remote is that in remote plasma enhanced, the plasma is above the wafer, and the wafer stays relatively cool. You have plasma, it's going to get hot, but it's relatively cool as a comparison. And then why is plasma enhanced chemical deposition beneficial? It's because the reaction takes place in the plasma. You can get much higher temperature, make the reaction go much faster, be very beneficial. And then also, like I just got through discussing, in remote plasma enhanced chemical vapor deposition, you can keep the substrate cooler. And then one particular application of plasma enhanced chemical vapor deposition is diamonds. You can use an inert hydrogen gas and methane, and you can, the microwave assisted plasma enhanced chemical vapor deposition. And these diamonds are used in many industrial processes. That's diamond blade down there. This demonstrates the different wafers with different kinds of diamonds. And it used to be that all the diamonds were impure or blue or black, and they looked awful. But in modern times, we've perfected the process a bit, so we can get diamonds that are actually aesthetically pleasing, and we can use diamonds produced by this method for recreational purposes, aka rings and other jewelry. And then another application of plasma enhanced chemical vapor deposition is semiconductors, where you can use dichlorosilane and silane and inert gases and have a reaction, and it's used very commonly in a lot of semiconductors. And then, of course, the whole reason that this presentation was started, you can use plasma-enhanced chemical vapor deposition to form carbon nanotubes, CNTs. And this is just a process diagram, a diagram of the process that is used, which is general hydrocarbon gas and catalyst, furnace, and then you have your nice bubbler because the stuff that comes out on the end isn't nice and you don't want to get it out into the environment, so you have a scrubber or other such device to clean it up before you send it out into the world. And this is just a demonstration of how carbon nanotubes can be formed. It's showing the little sp3 carbons and their reactions, and this is a metal substrate. They use different kinds of metals. So this is a metal substrate that's used. And this reaction can take place in two different directions, kind of. It can either start on the metal and go up and form the carbon nanotube, as this diagram shows, or it can start under the metal and push the metal up, forming the nanotube underneath itself. And this is a really zoomed-in microscopic picture of what these carbon nanotubes actually look like. You can see them coming off the substrates, or the substrate on the end of them. And very interesting, shows that it actually works. And this is a live picture of what carbon nanotubes look like that are generated from this process. It's kind of much more difficult to see that the carbon nanotubes just kind of look like dust. And then, because I wasn't really sure how to wrap up this presentation, just thought I'd give you a little taste of what might come for future applications of chemical vapor deposition. We could have improved diamond coating for industrial applications, much better knives and cutting processes and all of that. Thin film crystalline solar cells, so that our solar panels that we make can use fewer natural resources and fewer of those really rare chemicals that we need for other things that might be